To start off, what is a proposition? Well, a proposition is a statement which is either true or false. For example, there is a CSM midterm, and it's a proposition that's true. And there are some logical connectives between two different propositions, P and Q. P implies Q. If P then Q, P implies Q. P and Q, P or Q, not P, and P if and only if Q. Or you can also say P just in case Q. I think if and only if it's way more common. So what are truth tables? They just list the truth value of a proposition for every possible combination of the truth values of its atomic propositions. It could be used to show logical equivalence. I think if I press next, that would be a combination. Perfect. Yeah. So for every possible combination, P and Q, you just write out if P is true and Q is true, then not P is false. P and Q is true, P or Q is true, P implies Q is true, etc., etc. Yeah. What are quantifiers? A predicate is a phrase that describes a property of an objective or a relationship between two different objects. For example, P of X can mean X is even, and you would fill in X. Or L of X and Y is person X loves person Y. And you fill in the blanks with objects in our domain, which is the set of all things we're considering to get a proposition. So for example, and for quantifiers, it's about our set of our objects in our domain. For example, if it's for all X, P of X, it's true for all X, P of X is true. So P of X is true for all X in our domain. This backwards E means there exists some, we use a different variable name here. There exists a Y such that Q of Y is true. And this just means at least one is true. So it doesn't mean all of them are true, but it just means. So order definitely matters. For all X, there exists a Y such that P, X and Y is not the same as there exists a Y for all X such that P, X, Y. For example, if we use our example or our previous L and we say that, let's say our set of domain people all in this room, this first this first proposition for all X there exists a Y. That means for everyone in this room, we all love someone, right? L is X loves Y. But if it was the other way around, if it was for there exists a Y such that all X and L, X and Y, that means there is someone that everyone in this room loves. So it's two different things, right? Oh, this is the next slide already. Oh, okay. Okay, perfect. And here are some propositional logic tips. Here are some useful equivalences that I recommend you guys write down on your cheat sheet just to get it really fast on the midterm. Some pretty straightforward conversions. Here we use De Morgan's law where you move the negation inside and flip the quantifier. To check logical equivalence, you just substitute non-logical equivalence, or you could write out a table. I know a common example or problem on the midterm is they'll give you a set of propositions, and then you just iterate through each until they ask you, oh, what's the value of this unknown proposition? They give you several other propositions, and you just iterate through them all. And you could use a truth table. And you should also know what domain you're quantifying over. N is the set of all natural numbers. Z is the set of all integer numbers. Those two are the most common. You should be a little bit aware of all the rest of these. And to work with multiple quantifiers, you read it out in English. Like I said, like L, X, Y, X loves Y. And you could also use the Morgan's law to move negations around, which makes the proposition easier to read. And yeah, and you can also do techniques, which is our next topic. So let's start off with a simple example. What is the negation of A implies B and B implies A equivalent to. I'll give everyone just like maybe like 1 or 2 minutes to work on this. But it should be pretty straightforward. It's pretty straightforward. No need to spend too much time on this. You just use our previous substitutors. For here, you write out, and then you simplify the implications, and then use the Morgans to move the negation. Yeah, and then you just simplify again. Pretty straightforward. If you guys have any questions, feel free to ask, but if not, we're just using basic definitions here. Right. I'll give you guys some time to write it down. Yes?
Negation will only distribute to the like parentheses that are directly next to it, correct?
Yes. So, for example, here, everything inside this negation will distribute, right? So you negate here in this parentheses, so that's why it moves to this term. And then you negate the and to make it an or. And then you also negate this term and it's a different negation.
I guess this example makes sense, but in some I'll see like a proposition and then one right next to it. So it's like 2 parentheses next to each other and nothing in between, and then negation. So I'm not sure if that negation will apply to both or just the first.
It's just the one next to it, the negation sign. So it doesn't do it all the way through.
Oh.
Yeah. Mm-hmm. Good question. Right. Is everyone good? Next, okay. On to a more tricky topic, proofs. So more on implications. A lot of theorems in CS70 are in the form of P implies Q. And usually we want to prove that if we have P, then Q is also true. And you should be comfortable with these terminology. The contrapositive of P implies Q is not Q implies not P. And this is logically equivalent to P implies Q. We also have the converse, which is you just swap P and Q, where Q implies P, but this is not logically equivalent. And from P implies Q and P, we can conclude Q. And from P implies Q and Q, we cannot conclude P. So this is what I mean when I said there's usually examples on the midterm where they give you, 2 propositions and they ask you like, what's Q, right? So here, if we know that P is true or we know that P is true and P implies Q, then we know that Q is true. On the midterm, there'll be a lot more propositions, but this is just like a simple, straightforward example. And here are some more other English translations of P implies Q. If P, then Q, Q if P. You guys should be a little comfortable with this, but I don't think it's really too necessary. They won't try to trick you with English translations usually. Yeah, further, there are usually 4 general types of proofs. A direct proof, you just assume P, then derive Q. For example, if X is odd, then X squared is also odd. You just write out the definition of a variable that's odd, which is it could be written in the form of 2k plus 1. You square it, and you also show that it could also be written in that form for another integer, where the integer is 2k squared plus 2k. Contraposition, which is for all these cases, they're asking you to prove P then Q, but here you assume the negation of Q, not Q, then derive not P, right? Because those are logically equivalent. Same if they ask you here if x squared is odd, then x is odd, you just swap them, negate them, and yeah, root x is even here. 2k squared equals 4k squared, and yeah, 2 times 2k squared is even. Contradiction, prove p, assume not p, then derive contradiction. Here, I like writing it out as, sometimes they ask you prove p. Ooh, see a way to make it thicker. P then q. Then the negation of this is if you use all the definitions we talked about before, it's actually equivalent to p and not q. So this is the thing you assume if if um if you want to use or prove p implies q using a contradiction, right? You assume p and not q, and then using that you calculate a contradiction. And you can also prove by cases. And it says as proof q, and then you show that all cases imply q. For example, if the set was the set of all positive integers, you could prove a case where each integer is even and each integer is odd, right? And that would cover all the cases. Here's some general tips. Know what you're proving, be comfortable with mathematical notation. This notation just means that there is an integer q such that b equals aq, aka a divides b. If you're not sure where to start, just plug and chug. Start with simple examples, numbers, truth values. And proving existence, you just need to prove one example. And if they ask you to disprove a universal, just one counterexample, right? Because that would violate the universal. If they're asking you to prove p if and only if q, then you need to prove both ways. You need to prove if p then q, and if q then p. You can't just do a p then q. And you should assume what you're trying to prove because that's circular reasoning. It gets you nowhere. Next. All right, here's a sample, a question. For any integer x squared has a remainder of 1 or 0 when divided by 3. Yeah, you guys should definitely try this example. I'll give you guys maybe 4 minutes. And if you guys need a hint, just look on the board. Okay, I think we can come back unless you guys want more time. Anyone? You want more time? I'm good. Oh, you're good? Okay. Um, okay, I think that we're good to review it. So here, my hint was you want to tackle this with a proof by cases, and there are 3 cases here. For every integer, you could write them as representation. Case 1, it could be represented by 3k for some k in the set of integers. And we see that here, 3k is divisible by 3, and or x equals 3k, sorry. And then x squared would just be 3k squared, which equals 9k squared, which is 3 times 3k squared. And you see here that x squared is also divisible by 3. Case 2 is that x can be represented by 3k plus 1. And x squared here will be 3k 1 squared, which equals 3. Squared. Let me factor this out. Let me just look at the solution real quick. I think I messed up here. Oh wait, yeah, because okay, I don't know why I didn't read the problem, right? But it has remainder 1 or 0. I was a little worried because we had a leftover 1, but we see here that when we divide this by 3, we have a remainder of 1. So yeah, this case also works. And then the last case is just that x can be represented by 3k plus 2. It's more the same thing. You just go with a direct proof. No need to spend more time on this. Here's the solution you guys wanted. Yeah, so in this step, we broke it down into 3 cases, and then we just applied direct proof on all 3 cases. And because each of these cases cover the entirety of the set of integers, we know that we've proven this claim, right? Because like you said, or like I showed with this hint here, you could represent any integer using this format, either 3k for some k instead of integers, 3k plus 1, or 3k plus 2. And that would cover all integers in the set of integers. And any questions? No? Okay, let's move on. Here is another proof. Prove that given any 12 distinct integers between 60 and 80 inclusively, that is from the set 60 all the way to 80, you could find 2 integers whose difference is exactly 10. When you read this problem, it seems very intuitive, but we want to formalize this in a proof. Feel free to start. I'll give you guys maybe 2 minutes. And if you guys need a hint, just look up at the board. Yes. Or if you guys commit it to memory, which is better. It's more of a intuitive concept, but if you guys find that you sometimes forget it. Yeah. I find sometimes writing an example where you use the pigeonhole principle also helps a lot because it's easier to understand when you apply it.
Can't select multiple the same number.
Yeah, 12 distinct, sorry, integers. Yes. Maybe one more minute. Okay, I think we're good to go over this problem. So here, the hint that I'm giving you guys is we have to use the pigeonhole principle. So I asked the question, how many pairs are there of numbers where the difference between them is 10? Yeah, that's a question to you guys. Sorry, I should phrase that better. How many pairs are there where the difference between them is 10 in the set from 60 to 80? Exactly, right? There are 11 different pairs. For example, '60 and '70. Mm, 61, 72, and etc. all the way to 70 and 80, right? And because you are given 12 distinct integers, due to the pigeonhole principle, there must exist a pair where both elements are fulfilled, right? Because if you only had 11 distinct integers, you could put one integer in each pair, and there won't be a pair where two integers are different, whose difference is exactly 10. But because you're given 12 distinct integers, one of these pair must exist. You don't know which one, but you know that one must exist. Does that make sense? Sweet. Yep. See, here's probably a better, more formal answer. You can find 11 buckets where each bucket is the numbers whose difference is 10. So you have 11 buckets, but we were given 12 numbers. So by the pigeonhole principle, one bucket will have two numbers. Thus, we have two numbers whose difference is 10. Now moving on to induction. So for the overall scheme of induction, we want to prove that a claim P of n is true for all for a set of domain. It doesn't have to be all natural numbers n, but it usually is. Our base case is proof that the claim is true for the smallest number. Usually P of 0. It could also be P of 1, depending on your problem statement. The next step, our next step is the inductive hypothesis, and we assume that this claim is true for some number k. And our inductive step is prove that the claim is true for k plus 1 using our inductive hypothesis. Sometimes we want to use strong induction when regular induction doesn't work, and we assume that for our inductive hypothesis, it's the P of n is true for all n that is between 0 and k. Yeah, and it lets us use cases smaller than k in our inductive step. For example, if we want to prove, if we had a proof involving Fibonacci numbers, we would need P of k minus 1 as well as P of k to prove P of k plus 1, right? Because short demo, if for Fibonacci, it's P of k plus 1 was P of k. It's P of k. Right. If we had regular induction, we wouldn't be able to use P of k minus 1, right? Which is why we need strong induction here. And let's reiterate, it lets us prove statements that we cannot prove using weak induction.
Can you just always use strong induction?
Yes. It's just
Just write the assumption is that even if you use the
yeah, strong induction. Yeah, strong induction always works. So tips for induction, you want to always label your base case, inductive. Oh, yes.
Question about the induction earlier.
Mhm. Oh, like this example.
Or like the slide here.
Mhm.
Is it enough to transform your inductive step back into the inductive hypothesis, or do you have to use the inductive hypothesis to somehow prove like if you have some equality, your inductive hypothesis, and then your inductive step replaces the k with k plus 1.
Yeah.
Can you transform that inductive step into your inductive hypothesis to prove your claim, or do you need to somehow use the hypothesis in the proof to reduce it? If that makes sense.
That's a good question. So usually we always want to use our inductive hypothesis in the inductive step. So yes, we massage the P of k plus 1 to somehow look like our P of k so that we could use our inductive hypothesis. But in this case, you also have to make another claim or assertion that the remaining step or the remaining factor that we separated out from P of k plus 1 to get P of k is also valid, right? Because usually we can't somehow just magically make P of k plus 1 into P of k and call it a day. We also have to account for that other factor. I'll talk more about this in an example. It's easier to demonstrate there. Mm-hmm. Any other questions? Okay. Our tips, always label your base case, inductive hypothesis, and inductive step. You always get some partial credit. Make sure you use your inductive hypothesis in your inductive step, and you could also use other proof techniques to prove subclaims. And like you said, if you need a case smaller than your P of k in your inductive step, try strong induction. Usually for graphs, I think Leary will go into this more in depth later, but you want to start with a k plus 1 graph, then you move a vertex or an edge to get a k graph, and then you say that that's valid because of your inductive hypothesis, and then you restore the vertex and edge and show that that case also is valid. Yeah, for P of k plus 1. and you don't want to use build-up error. An example of build-up error, sorry, is let's say you're inducting on the number of vertices, and a property for the graph is that it's connected, right? Build-up error is you saying that when you add a vertex into that graph, the graph is still connected, right? That's not always true. That property can be violated if you add a vertex. All right, let's say this is your graph, you add a vertex, it doesn't necessarily need to be connected to your original graph. Yeah, just a small example of build-up error. All right, on to our first question. We want to prove that the summation of I from 0 to n times I factorial is equivalent to n plus 1 factorial minus 1 for n greater than I for the set of numbers in the natural numbers. Yeah, let me zoom in so you guys can better see that.
It does not, it is of times.
Yes.
Do we get that funny formula for what factorials are, or?
Oh, the funny formula for things.
Summation notation, some way of representing a factorial summation. I bet you might give that to you, but I don't think they would just say throw you like that. Okay,
yeah,
that's good.
yeah. If you're stuck, you think of a hint to give you. If you guys are stuck, feel free to just follow along with me on the board. Okay, just to start us off, we want to show that our base case is true. So here, our smallest case is when n is 1. And I just plug in n equals 1, and I show that 1 equals 1 is true, and that holds. So moving on our inductive hypothesis, we want to assume that P of k holds. That the statement is true for k. And then our inductive step, we have to apply, or we want to show that the statement is true for k plus 1. So we want to somehow go from this statement on the left-hand side, to the right-hand side. And I start my proof with moving the k plus 1 term out. And then because I moved the k plus 1 term out, I see that one of my terms is now the exact form that my inductive hypothesis was in. So now I could substitute here, way I copy and paste here. I could substitute that in. Okay. Here. Right. I just use my inductive hypothesis. Maybe a better arrow would be. And then I could just move. I could just move some terms over, just so you guys could better see. Okay, 1 factorial minus 1. Right. I just move the term over and then factor out the k plus 1 factorial. Does everyone get that? Everyone with me? Please feel free to stop me if you have any questions. This would just be time -1 factorial -1, and k plus 2 times k plus 1 factorial is just k plus 2 factorial, right?
Why?
Oh, it's a good. Well, I guess I could illustrate this with a straightforward example, right? Let's say k equals 3, right? And k equals 1, or k plus 1 equals 4, and k plus 2 equals 5, right? If you have 4 factorial, hence k plus 1 here, and you multiply it by 5, that's just 5 factorial, right?
Oh, right, factorial is multiplication.
Exactly. Does that make sense? No, you're good. Don't worry. And this is just what we want to show here. We could just separate. Okay, I switched colors. Cool. +1. And yeah, we showed that the left-hand side, we start with the left-hand side. Right here, sorry. We start with the left-hand side. And then we showed that that it was equal to the right-hand side. So that concludes our proof. Yeah, any questions?
Did you get from just like k plus 1 factorial plus k plus 1 plus k plus 1 factorial minus 1 to the k plus 1 plus 1 times k plus 1 factorial?
One more time, sorry.
Or I think it's that third line after the one above it.
This one?
One above it. Yeah, how did you get from there to the one below it?
To the one below it?
Mhm.
Okay, I factored out these two set of terms, right? Because this is 1 times k plus 1 factorial, right? And it's added to k plus 1 times k plus 1 factorial, right? So if you were to see that there is a 1 in front, that this term times k plus 1 is this, right? And then this leftover 1 times this is this. So that's why I was able to make these two terms into this. It's just factorization. Does that make sense? Yeah, with induction, be comfortable with factoring things out, especially so you can manipulate the expression in a way that you could get what you want. Okay. Any other questions? I think we're going to skip this problem. We could do this problem instead. Prove that 2 to the n plus 2 plus 2, or 3 to the n, 2n plus 1 is divisible by 7 for all n is greater than or equal to 1.
One that makes group part exams.
I think you might be thinking about Sinclair. Sinclair.
No, not necessarily the one we have right now.
No,
I don't even
no.
want to think about it. What do you mean, Raul?
Oh, yeah,
thank God
sorry.
it's Raul.
Raul,
Okay, good.
sorry.
That's the example really hard. They're all work.
Sorry, did I scare you guys? I think I mixed it up because you guys have Sinclair right now, right? Or
Yeah, we have Sinclair.
oh, okay, yeah.
Yeah, he's the president of class. Yeah.
I'm just gonna start doing this in the interest of time. If you guys get stuck, feel free to look on the board. Okay, I think we could all come back to this problem. Our base case, we just show that this holds true for n equals 1, and I show that the statement is equal to 35, which is divisible by 7, because 7 times 5 equals 35. And then our inductive hypothesis, we assume this is true for some k, for p of k. And then for our inductive hypothesis or inductive step, we want to show that the statement holds for k plus 1. So I want to show that it's divisible for some j prime, where j prime is an integer in a set of integers. And don't mix up j and j prime up. They're just arbitrary or integers or arbitrary representation for an integer in a set of integers. They don't relate in any way. So I got to, I just substitute k plus 1 in, and then I want to somehow manipulate it so it looks like my inductive hypothesis, so I could use it here. So I got to this step. I moved a 2 out to get 2 times 2 to the k plus 2 right here. And then I also moved out a 3 squared to get 3 times 3 to the k plus 1. And here is the tricky part, I think. You have to be a little creative to see the proof. But does anyone have an idea of what we can do to this 9 so that we could get our inductive hypothesis and use it?
Oh, well, now I really couldn't tell, but now that you said that, maybe split it into 7 and 2.
Exactly. Right, because if we split into 7 and 2, now we can factor. Again, this is where factoring comes really handy. And what, this is just 2 times 2 to the k plus 2 plus 2 to the 2k plus 1. Sorry for my teensy handwriting, I'm running out of space. Plus 7 times 3 to 2k plus 1. Right, because all I did was I split it into 2 plus 7, and then I took these 2 terms, or this 2 here, and this 2 here, and then I moved them all to this one term. And we're left with these 2 terms, right? 2 times our inductive hypothesis, which we assumed was divisible by 7, plus 7 times 3 to the 2k plus 1. And here we could finally use our inductive hypothesis. We know that this is divisible. I won't write it out because we don't have any more space. This is divisible by 7. And we see that this term has a 7 here, and it's divisible by 7. So because they're both divisible by 7, the entire thing is divisible by 7, which means that this whole thing is equal to some j prime or j prime in integers. Yeah. Any questions? Some algebra, some factorization. If not, we can move on. This is our last problem. Consider a game in which 2 players takes turns removing any positive number of matches they want from one of 2 piles of matches. The player who removed the last match wins the game. Show that if the 2 piles contain the same number of matches initially, the second player can always guarantee a win. Here, I'll just tell you, you guys should use strong induction. I'll give you guys maybe like realistically, 2 minutes is not enough, but just in the interest of time, just to think about it. Yes. A direct proof.
Say that matches contain 10, for the piles contain 10 matches.
Mhm.
Player 2 knows that no matter what, on the set of moves. What, oh,
What? Yeah. What
never
is?
mind.
What are the set of moves you're talking? Mhm. Hmm. That's an interesting question. I think you could think about it. Again, there's never one right way of proving things. If you could explain your thought process in a way that makes sense, it's your method of proving it could also work. So you don't have to use induction here, but I think it's the most straightforward way of proving this. Okay, so let's go over this. Here I just defined n to be the number of matches in each pile. Base case n equals 1. If there are one match in each pile, the first person that takes the first match will lose because the second person can just remove the match in the other pile and win. So this is true. This holds. And then we assume, because we're using strong induction, we assume for all n between, this should say 1. Oopsie. Between 1 and k, p of n is true. And our inductive step is I just want to explain it. I don't really want to write. Let's say you have p. I will actually p of k plus 1, right? And the first player takes an arbitrary number of matches from one pile. Let's say r matches, right? We can show that if the second player takes the same r matches in the other pile, right? We now have or right in both piles. And because r matches is one is at least one match, we know that this has to be less than or equal to k. Right, because if you have k plus 1 matches and you take r matches, which is at least 1, we know that the remaining number of matches has to be less than or equal to k. So here we could use our inductive hypothesis, which assumes true for all n between 1 and k, to show that this is true. And then we just conclude the proof that, let's say the first player takes, in the case that the first player takes all the matches in one pile, the second player could just take all the matches in the remaining pile, and this would also hold. Does that make sense? Any questions at all? Oops. Okay. It's a lengthy explanation. Any questions, concerns? If not, I shall pass it on. Oh, yes.
The exam, how does it roll if you use strong induction? Just regular induction.
That's a good question. If for strong induction, you want to think about the scenario where you might need not just P of K, but several cases before that as well, right? So here, because um, it's an arbitrary R amount of matches, we don't know that R equals exactly 1, right? So we need all the cases before K as well, right? I know sometimes I think on one of the discussions when I took the class, we just tried regular induction and it didn't work. So we had to use strong induction. So it was just like brute force, like you just try strong or try regular induction first and then try strong. But yeah, if you get stuck using regular induction, try strong induction. So yeah, if there are no more questions, I will pass it on to Lyria for stable matching.
All right, I will be taking over now, and then we're going to go through stable matching. We are a little bit tight on time, so I'm going to try to go through this as quickly as I can. So the basic ideas of stable matching are you're trying to pair two groups of job. Usually in CS70, they use the example of jobs and candidates. And the idea is that you want to pair a job, every single job with every single candidate so that each one has a pairing, and you want it to be a stable match, meaning that every pair is happy and they don't have someone that they would prefer more than their current partner. And also have that person that they prefer them over whoever they're paired with, which if that happens, it would be called a rogue couple, and that would not be what we want in a actual stable match. And so the algorithm, how it runs is every day, each job will propose to its favorite candidate. And then if the candidate accepts the offer, that they will have a little pairing made. And then what happens is that candidates will hold their offers that they have until they receive something that is better. And this continues until every single job. If a candidate rejects a job, then the job proposes to the next candidate on the list. So the algorithm keeps running until every single job and every single candidate has a pairing. All right, and then let's just do a very quick example. The arrows on the side are a little bit confusing because they're part of the animations on the slides, which we don't have right now. So I'm just gonna write it out like this. So these will be the jobs, and then these will be the candidates. And then they're all ABC. So on the first day, we're going to have the jobs send out offers. If you look at the ranking of the jobs, so they're all gonna first propose to the candidate that they have first. So approximation is going to propose to Anita. Basis is going to propose to Bridget, and then control group is also going to propose to Anita. And then what Anita is going to do is she's going to look at her listing, or let me get this out of the way. She's going to look at her rankings. So that's what's shown in this row over up here. And so she puts basis before approximation, but basis are not proposed to her. So she is going to choose the next one on the list, which is approximation, and then she is going to reject control. So now we can just take out this arrow because they rejected control, and then we're going to go down, and then we're going to see who control is going to propose to next. And then so control is going to get an offer to Bridget next because Bridget is up here. And then Bridget's going to take a look. So right now Bridget has offers from basis and control, but Bridget prefers basis more, so she is not going to accept the offer from control. And then so on the third day, control only has one last candidate, who is Christine. So control is going to extend the offer to Christine, and then this will be our pairing. So A will be paired with A, B will be paired with B, and then C will be paired with C. All right, and then just some important definitions real quick. So stable matching is just a matching that does not have a rogue couple, and a rogue couple is defined as a job and a candidate who would prefer someone else out there, and then that someone else that they prefer also prefers them more. So they both like want to be with each other instead of whoever they have now. And in that case, they would just choose to be with each other. Under the stable matching algorithm, there's no way to get that rogue couple because from the start, they would be paired with each other first. And yeah, so when a job is the one proposing, it would be optimal for the job because they can go down their list of candidates in order of their favorite to their least favorite. And then so yeah, it's optimal. The algorithm is optimal for whoever is extending the offers because they get to make the choice of seeing who they want to extend the offers to. And then yeah, so it would also, because it is optimal for the job in general, it would be pessimal for whoever is being asked because they have to wait for the job to extend the offer before they can actually even like make a decision. So it would be pessimal for the candidates who are getting the offers extended to them. All right, and then some important facts. This algorithm is guaranteed to terminate, and then it is also guaranteed to output a stable and job optimal pairing, and it will be pessimal for the candidates. And then there's also a very important lemma that you will use in a lot of stable matching proofs. It's the improvement lemma. And then so what this means is if a candidate gets an offer from a job, the candidate or the job that they end up with is going to be at least as good as the job that they currently have because they're just not going to accept the future offers if the future offers aren't as good as what they currently have. All right, and then let's just move on. So we have a quick question. Whose prospects get better over time and whose gets worse? And then, yeah, for this question, it's just like a pretty, it's like a kind of a conceptual question. And the idea is that because jobs are proposing and then they're going down their list of who they like first. So there's only downhills from there. So the job will have prospects that get worse over time. And then the candidates will get prospects that get better over time because otherwise they just won't accept the job offer. All right, and then they ask for a proof for the improvement lemma. In general, the exams aren't going to ask you to do this, but the idea is just that they just won't take the offer if the one they get offered isn't as good as the one they currently have. So it's only going to get better because the job is not going to leave until the candidate gets something that they like more, and then they will reject the job. So the idea is just that every job offer that they accept is going to be better than what they currently have. And so it keeps on improving. All right. And then, yeah, this is just a solution. All right. And then just another question. So imagine that all jobs have the same preference list of candidates. And so let's just say that like we have jobs A, B, C, D, and then their list of candidates are all 1, 2, 3, 4. Let's just call the candidates, label them by numbers. And then what they want you to prove is that the candidate, so which would be because 1 is the one that's listed first in every single job's ranking. So we just want to prove that the first candidate in the ranking has to be paired with her first choice. And we can prove that because assume by contradiction that this candidate is not paired with her first choice, but the job wants her and she wants the job more than whatever she's paired with because right now we're assuming she's not paired with her first choice. And then we would have a contradiction because that would produce a rogue couple, which would contradict what we have, the assumptions of a stable match being that the stable match does not have any rogue couples. And so here we have proof that the candidate first in the ranking will be with the job that they like the most. And also just intuitively, when all the jobs extend the offer to the first candidate, the candidate is going to accept whichever one they like the most and then pass on the other ones. And it's just not going to change because the job also likes that candidate the most. All right. And then
prove that from like directly from the beginning. So if they propose to this one candidate in the beginning and by the improvement level, they can't, there's nothing that's better for that candidate. It's first day.
yes, you can, or the improvement lemma is just saying that the offers can only get better from there. I guess if you did want to use the improvement lemma in this proof, you can say something like because they're already with the favorite job, So, and then by the improvement lemma, you can't get something that's worse because the offers can only get better. Yeah, so it doesn't change from there. Is that what you're trying to say?
Yeah.
Oh, okay, yeah, perfect. Yep, you can also say that. Yeah, and then the solution, they use like the proof by contradiction, which I talked briefly about earlier. All right, so that's stable matching. And then now we're gonna go into graphs, which tends to be a bit more of a trickier subject in CS70. But here is just a basic overview of some important things that you need to know about graphs. So up here is like a very helpful table that I would actually recommend you put on your cheat sheet because it has the definitions of like all the different kinds of traversals that you do in this class. So first we have the walk, which is note that you won't have any repeated edges. You don't have, or it doesn't require that you have any of these conditions, like anything, as long as there is an edge from a node to node, you can just like walk it. Just think of when you're walking around, as long as there's a path, it constitutes a valid walk. You don't have to end up somewhere. You don't have to, there's no conditions that you have to like, you can't repeat a vertex or you can't repeat an edge. So the walk up here is just clear. It doesn't check off any of these boxes. And then for a path would not want you to repeat any vertices, and it would also not want you to repeat any edges because if you think about it, when you're taking a path, you want to get somewhere efficiently. So you don't want to be taking the same or going back to the same spot or going through the same edge because that would just be like repeating your path. So a path would, yeah, the conditions for a path are just no repeated edges and no repeated vertices. And then a tour, the only condition for a basic tour is that the start vertex has to be the end vertex. But yeah, if you think about it, when you want to take a tour, you might like have more time. You want to see things around. So you can repeat edges and you can repeat vertices because you just want to end up where you started from. All right. And then we have a cycle, which is basically, it's like a tour, but you don't have repeated edges because I guess in a cycle, you want to think of kind of like a circular structure that goes around a bit. So you don't want to be like going overlapping an edge that you already went through. And then we have the Eulerian tour and the Hamiltonian tour. So it's basically just a tour, but it has the extra condition for Eulerian tours that every edge is traversed exactly once. And then for the Hamiltonian, it's every vertex is traversed exactly once. So you don't repeat those. Yep, question?
With a cycle, no, Eulerian tour, is it no repeated vertices is not checked off because you're repeating the start vertex, or are there other vertices that can be repeated?
You can in general repeat any vertex. The idea, like, let me just see if I can draw a quick graph structure. Let's say we have something like this, or no, that would not. Let me add something else. Okay. Does this work? Uses every edge. Yes, it does work. So like for this, if we wanted to run an Eulerian tour, we would start from this one. And then go here, go here, go here. Oh shoot, sorry. Started from the wrong edge. Started from the wrong vertex. Let me just. You would start from, let's say we start from this one. Sorry, 1, 2, 3, 4, 5, 6, and then you return back here. I guess this one, it only repeats. I can't think of a better example at the top of my mind, but you can repeat different vertices because if you think about it with like the ones with higher degrees, like let's say you have some graph and then let's say that these nodes, like let's just assume that the 4 out here branching out are connected somehow. But if you have like, you can go in and out of the vertex. And then the conditions, I will also give like a little brief rundown about the conditions that are needed for an Eulerian tour to exist on a graph. And yeah, but I'll get into that in just a bit. And then the Hamiltonian is it has to go through every vertex exactly once, and it has to end at not exactly once, but it has to start and end at the same vertex. All right, and then in general, in CS70, the graphs, unless stated otherwise, they are undirected, which means that they don't have like the arrows unless the problem explicitly tell you that we have a directed graph. And then it doesn't have any self loops. A self loop is like a vertex that has an arrow going back into itself. Yeah, so graphs would not have that unless, or yeah, I don't think any questions I've ever seen in CS70 has had a self loop. And there will also not be multiple edges between the same two vertices. So only one to a vertex. But all right, and then the degree is the number of neighbors for a given vertex. Like for instance, let's take this vertex right here. Does anyone just want to raise up fingers about what degree this vertex is? Yep, perfect. It would be 4 because there's 4 edges going out of it. And then the total degree of the graph is the degree of every single vertex added together. And it's fine to repeat the edges because the idea is that after we count the total degree, so this vertex has degree 4, this vertex has degree 3, this vertex has degree 3. We add them all together to find the total degree of the graph. And by the handshake lemma, which is stating that since every edge is connected to exactly 2 nodes, so it adds exactly degree 2 to the total graph.
That was the degree sum theorem.
Huh?
That was the degree sum theorem.
Or it's, yeah, it might be called a different name, but because of the handshake lemma, this holds. Yeah. All right. And then, yeah, these are just some like other important properties of graphs. So connectivity, a graph is connected if there's a path between any 2 vertices. So you wouldn't, yeah, like for instance, if we have something like this, that would not be connected because you can't get from this vertex over here to like this vertex. However, if we just add an edge over here, that would be connected. All right, and then the conditions for an Eulerian tor, as I stated earlier, is it exists if and only if every vertex is of even degree and the graph is connected. So every vertex has to have an even degree, meaning that like it either has 2, 4, 8, 10 edges going out of it. All right, and then coloring, when you color graphs in general, unless they're saying you're coloring by edge, otherwise you're coloring by the vertices. So right now, this is 2 colored. You're coloring the vertices and you're making sure that every edge does not connect to vertices of the same color. All right, and then a bipartite graph is if it can be, it's basically if the graph can be 2 colored. So yeah, it's just we want to know if a graph is bipartite because we want to know if we can split the nodes into 2 distinct groups that do not have a connection to each other. And then a complete graph is where every vertex has an edge to every other vertex besides itself. So some well-known ones are the K5 graph, which just it looks kind of like this. So every vertex, there's 5 vertices in total, and then every vertex has degree 4. And just recall, since every vertex has degree 4, an Eulerian tor would be possible on this graph. And yeah, a tree graph is just a minimally connected graph with no cycles. And then every single time you have a tree with a total of n vertices, the number of edges will be n minus 1, no matter what kind of a tree you have. And then recall that a hypercube is essentially a structure which it's a graph where it assigns each vertex a n-digit bit string. So let me just do the very basic case of a 2-dimensional hypercube. So we would have, let's say this is 1, 1, this would be 0, 1, this would be 1, 0, and then this would be 0, 0. And then you connect all the vertices that differ by exactly 1 bit. So you can connect these 2 because they differ in their second bit. You can connect these 2 because they differ in their first bit, connect these 2 because they differ in their second bit, and connect these 2 because they differ in their first bit. And then so that is the 2-dimensional hypercube. And for planar graphs, there are some conditions here. I would recommend also putting these on your cheat sheets. But in general, when you want to prove if a graph is planar or not, you see if it contains this K5 structure, which I drew out here, and this K3 structure, which let me just draw out really quick. And then I think there's. Yeah, I think that is the structure. So you just, when you want to, if you want to prove that a graph is not planar, as long as you can show that this K33 or this K5 is included as a subgraph within that graph that you're trying to prove is not planar, then you can show that the entire graph is not planar. All right, and then now I'm gonna be showing like a counter example of what you should not do when you're doing graph proofs. This is what Keem talked about earlier regarding the buildup error. So I'm going to be showing a classic example of how buildup error can form and then how we can avoid it. So this right here is just a false claim that we have. And our claim is that if every vertex in an undirected graph has degree at least 1, then the graph is connected. And obviously we know that is false because let me just draw out a really quick structure right here. Like if we say that this is the graph right here, it is not connected, but every vertex does have degree of at least 1. Okay, and then, but when we do like the induction with buildup error, there's a way to actually say that this claim is true. So that is an example of how buildup error can create us it can prove a false claim. So I'm just going to briefly go over how that happens and how we can avoid it. So right here we have the base case, which is this is the induction with the buildup error that I'll just show real quick. So right now the base case is that we just have one vertex. It doesn't have any or let me just say our base case is this. So every vertex in this current base case graph that we have has degree at least 1. And then the graph is also connected. And then inductive hypotheses is that assume that it holds when no matter how many vertices we have, like for n vertices, we're just assuming that they're all going to be connected. And then inductive step is assuming that this right here is true, that we can just add another vertex. And no matter how we add the vertex to the graph, it kind of holds and it stays connected. But the issue with this is that there's different ways you can add the vertex. You don't necessarily always add it being connected to this graph. You could also add it as like a separate vertex, and that would not be connected. Or I guess right here, the buildup error is that because you have to keep the vertex you add with, it has to have a positive degree. So it's forcing you to connect it to another node on this graph. Otherwise, it wouldn't have a positive degree. But the issue with that is that like technically when you're building the graph, you have that restriction, but you can fulfill the restriction of having a positive degree if you're adding like 2 vertices at once and you connect those 2 together. So essentially the idea is that you can't just directly like add it in because you're not considering all the different cases of building up a graph. So idea of how we would prevent this buildup error is we start actually with a n+1 graph like this one. Let's call this the n+1 graph. It has n+1 nodes if we're assuming that this is the n graph, this is the or we have to assume that it's connected. The idea is that we want to show that when we have an n+1 graph, when we remove, let's say that this is the n graph that we're assuming is true. When we have the n+1 graph, we want to first remove a vertex, and then let's remove this one here. And then you have to somehow be able to construct the base case, but because of the way we removed it, we're not able to get the base case to show up in here again. So it's not a valid inductive proof because there's no way to reconstruct this base case if we're like choosing a certain way to remove the vertex that was up here. So there's no way to prove it. And that's why, when we're doing graph proofs in general, we want to start from n+1. We want to show that we can construct the base case. And then, or there's some way to always be able to construct the base case under different circumstances. And then we build it back up to show that it holds. And I'll show like a little example of this. in this problem right here, oh, they already show the solution, so I'm gonna just swipe up here and not show the solution. And then, yeah, so this question, it appeared on one of our discussion worksheets or our CSM worksheets in the past. I don't know if you guys remember though, but it's just trying to prove that when you have because we know that we have a connected structure. So let me just read through the problem really quick. You're at a party where a person is only allowed to come if they are friends with at least someone else, at least one other person in the party. And then no one is friends with everyone else. And there are also only a total of n-1 friendships. So what we have here is we have n people, but n-1 friendships. So for it to be connected, it does have to be a tree structure. There's no other way to have n vertices and n-1 edges and have the graph still be connected unless it is a tree structure. So right here at the top, we know that it's already a tree structure that we have. Let me just draw like an arbitrary tree that we will be using for this. And then the idea is that you want to be able to split people up into two teams where no one is friends with anyone else in the team, which is possible because this tree right here, the hint down here is that we want to prove that a tree is two colorable, which I'll do real quick. But yeah, after we do that, you can just prove that you can two color the nodes. So the pink nodes will be put in one group, the white nodes will be put in another group, and no one will know, will be friends with someone else in their group. And then, yeah, I'll now do the very quick proof about the tree being two colorable, because that would be a graph induction proof that can kind of show us how we can avoid the buildup error. So base case is we just have one person. So one person. Let me make this a little thinner. Base case is we have one person. And then, yeah, we can split that off into two teams. So one team, or let's just, or yeah, we can arbitrarily split them into two teams because we can just put this one person into one team and then the other team will have no one. It is possible to split it into two teams though. And then the inductive hypothesis is that there's a way to color any tree with k vertices. Or for consistency, I'm gonna, instead of calling this one person, I'm gonna call it one node. And then it's gonna be its own tree structure. All right, and then now we want to do the inductive step, which is proving that this holds true for k+1 vertices. And then how we would do that is we first construct a tree with k+1 people. And then we're gonna take someone out. Like let's say we're gonna take this person out, right? So we're gonna get rid of all of the nodes and the edges attached to that person. And right now we still have different tree structure. Oops. We know that a tree, when you remove a vertice, it will just create more trees because each one of these, like the little individual ones, they're like its own node, which we are arbitrarily defining as like a valid tree because it can be colored. And then the other ones, this right here is also a tree, because a tree, like as long as it doesn't have any cycles and everything is connected, is considered its own tree. For the disconnected ones, we consider it its own tree. So there's always ways to construct that tree. And then we're going to use the inductive hypotheses. So we assume that all of these trees are two colorable. And then now we want to add the person back, but you can show that no matter how, or you have to add the person back in a way so that everyone is connected again. It doesn't really matter how you do that though. I guess in this case, there's only really like, oh, I guess you can connect it like that. You can also connect it to like any vertex up here, any vertex. Yeah, any vertex on the side. It just has to continue to be a tree structure. And then you can show that because we're assuming that the trees are two colorable, so no matter which tree you connect it to, no matter which node, as long as you just flip the colors underneath that tree, they are going to still be two colorable because each one is already two colorable, right? And then so when we connect it back together, you just have to flip the colors if the colors are the same with the one that you're connecting it back to. And then so, yeah, the idea is that since after we connect the tree, no matter how we put that person back in, no matter how, it does take into consideration like all of the different ways you can put that person back in. So it prevents the buildup error because we're taking all cases into account rather than just assuming like we did earlier in the case that is a false proof with the buildup error. Instead of just assuming that we're putting it back a certain way, we're considering all cases across how we're doing it. So it prevents the buildup error and it gives us a very rigorous proof that we can work with. Does that kind of make sense, or any questions about this? Yes.
It's more general, but all trees would be planar, correct? Because
Yes.
they have all those planar.
All right. And then,
This case for area.
Or
It was implied, linearity implies the formula is because it works both ways.
Well, I think you can.
It makes both ways.
It's like, you can prove like the K5 is not.
That's the first direction of the.
Yeah, like it doesn't work with like P plus ten. It's not.
That's still the fourth one.
Well,
You're taking a graph versus the formula, change formula.
I think as far as I remember, I don't think you can go from the formula to prove planarity.
Only one.
Yeah, I think it's only one direction. Like if it's planar, it will uphold
Okay,
this
so you're
formula,
taking-
but the
you're
formula
taking
doesn't necessarily.
Do with all this.
Yeah, for planarity proofs, I recommend, I guess you can always check if it upholds the formula or not. If it doesn't, then you definitely know that it's not. But if it does, it doesn't necessarily imply the graph is planar. You would still have to show like the graph contains a subset of K3, or K, the complete graph of
So
K5.
given an arbitrary graph with the first level.
Yeah. Okay, and did I see a question somewhere here or no? Oh, question?
3B like E is less than equal to 3B minus 6. That's for all connected graphs, all simple connected graphs to prove if they're not planar.
Oh, see, like right here, what it says is on a planar graph, this statement always holds, but it's not sufficient for this statement to hold that, like even if this statement holds, it's not sufficient to just use this statement to prove that a graph is planar.
Right, but you can apply that to any graph as long as it's connected. Or like you can try.
Oh, yes, as long as it's connected. And then if you show that it doesn't prove, then you know for sure the graph isn't planar. Because if it's planar, it has to uphold this. But if it still holds, you can't just say that, oh, since it holds, we know that the graph is planar. It doesn't work that way. It's kind of like the square is a rectangle, not a square kind of thing. But yeah, the idea is you can use this inequality when we know that the graph is planar, or you can use the inequality to prove that a graph is not planar, but you can't use the inequality to prove that the graph is planar, if that makes sense.
Why can't it be used for like disconnected graphs? Like if you have vertices that are connected and then one isolated vertex.
Because then it doesn't, I guess let me see. It actually shouldn't make a difference because this on the right side, it's a upper bound for the number of edges. So if you have more disconnected components, I'm just trying to think. I guess the more or I wouldn't say intuitive, but I guess it would just make more sense to use it on one graph because when you add in like a lot of more disconnected components, I think it just makes, and when they usually say like for a planar graph, they're just implying to like one graph, one connected component. I'm actually not too sure if it will hold when you have more disconnected components, but,
Wouldn't like a disconnected graph, like as we keep adding vertices that are isolated, that inequality would definitely hold true for some amount of like minimum vertices.
yeah, I
Because the
guess
edges wouldn't
so.
change.
Yeah, the thing is, I'm just worried, like when we add more vertices, let's say we add 4 or 5 vertices and you add like a complete graph, that would screw up the inequality a bit. Oops, my complete graph looks awful. But I think it just makes, it's just more, I think, more confusing. And in general, I think they wouldn't make you prove that like a disconnected graph is planar, because it would make more sense for them to just ask you like if that one component is planar or not. Okay, and then let me go back. Let me also check on time. Oh, I think we're a little short on time. But this one, all the slides will be sent out so you can look at that. I want to leave some time for modular arithmetic. This one is just like some properties for modular arithmetic. So it will be on the slides. I recommend just putting it down on your cheat sheet, but there's nothing like too difficult over here. And then the Euclidean algorithm is used to find the greatest common divisor, which is useful. And then, yeah, how you run it is you just take 2 numbers, you take the smaller one, or you take the larger one and you mod it by the smaller number, and then you take the remainder and replace it with the larger number, and you just keep going until you get a remainder of 0. And the last non-zero remainder is the greatest common divisor. Yeah, these slides will be sent out, but because we are running a bit of short on time and we still have a couple of topics to go through, I'm just not going to run through this right now. And then the extended Euclidean algorithm, it's often used to find the inverse of a number in modular. And yeah, it's also just an algorithm that I believe you can find on past like CS70 discussions and worksheets. I'm also not going to go through this right now. And then Fermat's Little theorem, this one is pretty important, but it's also just 2 general equations that you will always use when you use Fermat's. One is, oh, and then P does have to be prime for the Fermat's Little to be applied. But as long as P is prime, it will hold true that when we have some number integer a to the power P minus 1 is going to be congruent to 1 under modular P for that prime P. All right, and then this is like the general idea of how the Chinese remainder theorem works. And then we also have like a quick Chinese remainder example. I will go through this really quick. So the idea is you take the ones that are modular, you check that for their first coprime, because you can only use the CRT when they are coprime. And then you're going to calculate the product of all of these moduli. So they call it M, and then they multiply them all together, and that is 132. And then you're going to calculate all of these. You're going to take 132 and you're going to divide them by all of these numbers here, which are the moduli. You're going to divide them by all of the moduli. So you get these numbers on the right over here. And then you find the inverse of these numbers under their respective moduli. So you're going to take this 44 and you're going to take the inverse in mod 3, because this 44 over here was created in mod 3. So each one like correspond to 1, 2, 3. And yeah, so you're just going to find all the inverses. And then what you can do is you then take, this is a little bit of a confusing process. I would recommend like writing down an example of the CRT on your cheat sheet if you don't think you can remember how to run it. But afterwards, the idea is, let me just erase all of this on here. You're going to take this number, this number, and this number, multiply them together and add them. And you're going to take, multiply them together, and then you're going to add, let me use a different color, this one, and this one. You're going to multiply those and add them to what the pink numbers that were computed earlier. And then let me get another color. And then, yeah, so that's how we get over here. And then after you add it all up, all of these multiplications and summations, you will get that this is 293 mod 132, which comes pretty cleanly to 29. And then so you know that 29 is the number x you're looking for that satisfies all of these equations. And all right, we have a very quick practice problem. I will give you guys like maybe 1 minute to look at this. And the hint is to use Fermat's little theorem. And recall that would be a to the p minus 1 is going to 1 mod p. And then we do know that 71 is prime. And then I'm just going to start working through it. I think in general, the most important part is just knowing how to use it and when to use it. I think that will come like as you do more practice exams. You'll see like certain scenarios where they want you to use a CRT, and then you'll get more familiar with running the algorithm. Yeah, just solving the modular equations is the most important idea. All right, since we're running short on time, just look at the board up here. So we know that because 71 is prime, we know that 21 to the 70 is congruent to 1 mod 71. And then so we can substitute that in to simplify eventually to 21 mod 71. So that would be the answer for this. Yep, and then that's just the solution. And then this one, let me see how much. Okay, this one last one. Let me just take 2 minutes to go over this really quick. So mod 150, you can right off the bat, you can see that 150 is just 15 times 10. But since they're not co-prime, you can't just do something, you wouldn't use the Chinese remainder theorem. So don't think about the Chinese remainder theorem for this one. Instead, you can think about how many different solutions under mod 150 would satisfy both of these equations. And then the idea is we want to find the least common multiple of these, because that would be the only way that, I guess it will make more sense as we see. But first, I'm just going to write out that the least common multiple is 30, because 10 divides 30 and 15 also divides 30. So that comes out pretty cleanly. And then now we can write x. We can express it as, so we want x to hold that x is equal to sum a plus 10. Let's call it I. And then we also want x to hold so that a is equal to sum b plus 15j. And then when we take the least common multiple of 30, we know that we want the general equation to look something like x is equal to sum let's just call it sum k plus 30 hold on, let me see. I'll just make it some other variable, because the idea with this is that this is like a general representation of equations that could also satisfy these, because when we have something that has a remainder of a when it's mod 10, and we have then when it's mod 30, it would also have like a certain remainder. So we just take x mod 30 and we see how many different values for that x can also satisfy the these equations up here. And the idea is that after we write out in this form, you can see that because 150 divided by 30 is equal to 5. So there's 5 different numbers that can fit within the modular 150 that would satisfy these equations. I guess the main idea here is just finding the least common multiple and then taking the total modular, dividing it by the least common multiple, and it's 5. So we can have 5 distinct solutions. I think the solutions down here might do a better job of explaining. Essentially, yeah, if you have like one solution, when you add 30 to it, it would still also be a solution. And then there's like 5 ways to do that within modular 150. So that's how they kind of proved it. And then the next part is, okay, if b minus a is not a multiple of 5, what is the number of solutions for x? And that would actually be 0, because in order for a solution to exist, b minus a has to be a multiple of 5. Because otherwise what happens is, yeah, since we're short on time, I'm just going to show you guys how they did it here. So they expressed x in terms of the a's, b's, and then plus another constant that they made up called k and k prime. And then they wrote it all out. Like when you subtract them, when you subtract one from the other, it should exactly equal 0. So they distributed it out, and then they showed that we have, it simplifies to b minus a plus 5 times 2k minus 3k prime. And then since we know this one is exactly divisible by 5, so if the entire thing is divisible by 5 in, if the entire thing is divisible by 5, then b minus a must also divide 5 in order for this statement to hold. Does that kind of make sense? Because we know that, or actually, let me see if there's a more clear way to write this out. Or yeah, I guess since you know that this divides 5, so b minus a, it would be equal to, or if you just distribute it and you put a minus b on one side, it's equal to 5 times 2k minus 3k prime. You know that if this side divides 5, then this side must also divide 5. So if, and then if a minus b divides 5, or 5 divides a minus b, then when you negate it, it would still divide 5. Or 5 would still be able to divide it. And yep, so that's the idea behind that. And I will pass it over to Robert now for the last topics.
Right, so I will go over a brief overview of just what RSA is. So basically, we got Alice, here's Alice, and we want to send Bob a message. So we'll call this message X. Here's Bob. And Eve, which we're going to put here, wants to see the message. Okay, we don't want Eve to see that. So what Alice will do is she will encrypt the message right here and send it to Bob so he can decrypt it. So what Bob's going to do is this. The message that Alice sends is here, and Bob is going to decode it. Now, Eve can still see the message, right? But she won't know. The idea is we don't want her to know what it actually is. As a crypt our message, what we do is this. So we choose P and Q initially. So the assumption is that Bob and Alice choose P and Q independently, and then they're gone. Like they're no longer using the process. Because P and Q are used to make N. N and E are the public keys of Bob. Now, E is relatively prime, or also known as coprime, to the product of P minus 1 and Q minus 1. So we're going to then go say that Bob's private key will be D. Now, private key is seen by Bob and Bob only. No one else access private key but Bob. What is the inverse of E mod P minus 1 and Q minus 1? So I might refer this to R just for simplicity's sake. So just keep that in mind notation-wise. And now we just reviewed the module section. In case you forgot, when we say inverse, what we're saying is like, if I were to say like X x is inverse of a such that a times x is equivalent to a mod n. That's why I say inverse. A few ways to do it. You got FLT, you got extending Euclids and other methods. So I will go to a quick proof now. That'll be pretty handy, and you'll see exactly why. It'll be very useful in an exam question of exam I took when I was in this class. So I'll probably want to go with these together. So just keep pace with me as I go through this. So you want to prove theorem 7.1 from your notes, which just says you want to prove the statement up here. Whoops. Yeah, I erased this. Go away. So under okay, so when it says about definitions, referring to the ones like pretty much these I've written to you before. So you want to say is that you have encryption, decryption, ED. If you were to decrypt E, you would get X mod n. That's the idea. So the way we will do this, let me just get rid of these guys. There we go. Okay. So what you want to do is to prove this statement, which is equivalent to the one above, because as we defined before, yeah, here it is. So defined before, we got EX is equal to X to the power of E, and we got dy is equal to y to the power of d. And so since we're plugging xe into d, we're getting the same result as the above. That makes sense. Right, let's double check. So since we know that d, oops, that's a very bad d. So you know d is inverse of e, as I kind of showed you above, we know this small fact. So ED is equivalent to 1 mod of R, where R is simply P minus 1 and Q minus 1. And so using this fact, we can also say, by definition, that is equivalent to 1 plus K times R. Does it make sense, the flow so far? Okay. Cool. And so from this, what we're going to say is that X to the power of ED is also equal to X power 1 plus K times R. And then, oh, wait, mod n. Whoops, I forgot to keep mod n. Does it make sense how we got to these two steps? Right, okay, I took way too much space. That is not good. Right, should be fine. Okay, so from here, what we're going to do is also keep note that we could subtract X on both sides. So we're going to do that right now. And you'll see exactly why we do this in a minute. Because if you notice that we have X on this side, we can actually factor it out and do X to the power of K times R minus 1. So the idea here is that if X is a multiple of, say, Q, so we're going to put two cases here. And since recall that N is composed of P and Q, there are two cases. So if we have it that X is a multiple of Q, then we know that this mod Q will be 0, right? This whole expression. I should probably write a little bit lower because I feel like you don't have enough space to see this. Okay, so back to this. Since we got the statement above, right? We're also going to say that looks good. Okay, I did forget to add one more note. Just I think this might be a little confusing now that I'm actually thinking about it. So recall that the original thing you want to prove is this, right? The reason I'm trying to show it's equal to 0 mod n, or at least mod q and p, is because we're doing e to the power of x to the power of ed minus x, because we're just subtracting x to both sides. And we're just trying to say this is equivalent to 0 mod n. And as we've shown before, since ed is equal to 1 plus qr, we got 1 plus qr and minus x equivalent to 0 mod n. And so back to what I was trying to do before, since we factor it out and we got this expression right here, and we got case of which we got, say, x is a multiple of, say, q, the expression will be 0 because q is a factor of n, also so is p. So by definition, this would be 0 or greater. So we're going to do next case, for which we're actually going to use a funny trick of FLT. So recall that in FLT, if I do a to the power of p minus 1, it's equivalent to 1 mod p, right? And so we're going to use it in our case here. Recall that for, okay, it's a little messy, right here. So you got x to the power of k times, say, p minus 1 and q minus 1. For both of these, we can simply do, let's say for an instance of q, we want to do q minus 1, k, and then p minus 1. This will be equivalent to 1, right? And so since we got 1 here, can you guys see this, by the way? I know it's like super, it's super small. Can you guys see it while I'm writing down? Or... Cool. Yeah. All right. Okay, so basically, we want to show that this is 1, right? So we can go down here and just say this is 1. And okay, that is x 1 minus 1, which is 0. And so now you got 0 mod n for both cases. And that, since both, and for both p and q, it's 0, we can also, by symmetry, say that it's also 0 for mod n. Then 0 for mod n are standard above holes. So that is how you prove this theorem right here, using these few RSA definitions. So any questions about this so far? Cool. Okay, so I'll move on to a test question in which you can use the exact theorem to actually get some points. So who would like to tell me for this question here? So consider RSA scheme with this public key and this private key. Recall that encoding of a message X is this, and encoding the decode is going to be dy to the yd. So does this hold for 5a? Yes or no? Using what we just proved. Any takers? Okay, so I will just skip to the answer right now. So, okay, I don't want to spoil too much. So it is true, pretty much for the theorem we just showed. Did you go further in explanation for this, or are you guys? Cool. All right. Also, if you also want to know just another intuitive thing, if you forget the theorem. Yeah. Makes sense. Cool. So for the next one, give an expression that decodes a doubly e to ex mod n, especially answer in terms of y. This would ideally be using these two functions. How will we do this? Any ideas? And why we just decode twice? Yeah. So I'll just spell the answer. Right. This is the very neatly written, I guess, with all these parentheses involved answer. But yeah, that's pretty much it. So for this one, wait, do you want to get part B, by the way? Is there any questions on that? Cool. All right. So part C. So we have A is equal to x to the power of e, b is y to the e. What will be DAB? What takers do we have for this? Like how will you approach this problem if you were to do it on an exam?
We write a times b is x times y to the e mod n.
What's what you said? X times. Yeah. Yes. Spell the answer. Yeah. So these questions make sense. You have any questions on them? Okay, is everything clear? Cool. All right, so there is some true and false real quick. So in RSA, is n prime. I'm going to zoom in a little bit because this is very hard to see. Is n prime? Why not? Yeah, that's false. If Eve knows p minus one, q minus one, she can solve Alice's private key. Yes or no?
Yeah.
Yeah. And why is that?
Because of private keys.
Yeah. So she used this. She can pretty much find the inverse and all that. That's like D and all that stuff. So that won't be good, right? Yeah, because D is equal to E mod this expression. So she has that. You're cooked. So the E in the public key must be the smallest number to P minus one and Q minus one for RSA to work. Yes or no? Well, what will be the benefit or the lack of benefit if you have a small or not?
Easier to compute. I don't know if it's important.
There's no difference. Yeah. The reason we only use small numbers because it makes our life easy, but like you're not strict to actually use them. I don't know why you won't use a larger number, but you can.
Right.
So next question. Alice can use her public key to secretly send messages to Bob.
Her own public key.
Yeah, can she use her own public key? Yes or no? And why not?
She's on secrets.
Yeah. Yeah, because Bob has his own public key, but his own private key, I guess that we D, whoops, that he can see. So only he has access to D, while everyone else has access to N. The reason people use the public key is to encrypt so Bob can see. And Bob has a decrypt key so he can decrypt the info. So next up, when setting up her public key, if Alice shares D instead of E, can you still run RSA scheme? Well, what will be the difference? If you switch up the key as well for Alice, so keep that in mind. Will this be any different? Because recall that D and E are inverses, right? And so in either scenario, it'll still be ED mod N, 1 mod N, right? So would it really be a change? There wouldn't. There wouldn't be any change to this. So if you want to switch them, theoretically you could. So if Alice somehow forgets the original P and Q to set up her private keys and public keys, can she always just use D and E to recover them? Is there any recovery mechanism to this? If I were to just give you N, could you somehow find me P and Q?
No.
Exactly. So because of this, you can't recover it. And the point is you can't recover it. If you could, they'll ruin the point of this game. And now the last one. Bob encrypts each character in the message and sends it to Alice one at a time. And is Eve able to completely compromise the message?
It's just the same thing as the entire message that you did it.
Yeah, so imagine I just sent like A, B, C. But recall there's only like how many letters in the alphabet, like say 26, right?
Yeah.
And if I just send one letter at a time, wouldn't she be able to also crack the code eventually? Because she already knows if she has an idea of what I'm sending.
Oh, is it, was it? Oh, that makes sense. That's true.
Sorry, you can explain that one to me.
Yeah. So basically, like Eve can also encrypt the letters, right? Like if you send a letter, she can also like do her own encryption. Key's public, right? Like, and it's a public key. She can encrypt, you can encrypt. And so she could just test out what it is for all 26 letters and just decrypt that way. If you're just saying one letter at a time. like if I send A, right? But both Alice and Eve can encrypt A the same way because using Bob's public key. You're getting the same result for both, and she can just see like what the encrypted value is. Like just say it's like 1, 2, 3, and both Eve and Alice get the same encryption. She can figure out what you're sending like that. Does that make sense? Pretty good. Cool. Any questions at all on RSA before I jump to polynomials? Or are we all good with it? Cool.
Are we gonna have, do you think it's probable that it's passing the exam, so like they run an RSA scheme?
At least something I think more conceptual, like this question. I think I don't think you have to run an RSA scheme in itself. No.
Okay, good.
Yeah, it's a little painful. Thankfully, you don't have to conceptually do it, but stuff like true and false questions like this, or questions like this that are a little more conceptual, you're likely to be expected on the exam. So just keep that in mind. I don't know what's changed this semester in terms of exams, so I can't determine that. For when I took it, you just had to know conceptually and you were fine. So for polynomials, if I say a d-degree polynomial, I'm just saying the first term is going to be, say, some coefficient times x to d, which is the d-degree polynomial, all the way up till your lonely coefficient a0. There are 2 rules you need to know. So a polynomial of degree d has at most d roots. Roots are just like in this guy, so on. Now, this is a very important one. A polynomial of degree d can be uniquely defined by d plus 1 points. This is going to be very useful when we get to stuff like secret sharing. It'll make sense as to why. Well, I'll just put interpolation as well, now that I'm going into it. So given a set of d plus 1 points, you want to create a polynomial of degree d which has all of those points. So recall this fact. Put it in cheat sheet, write it down. Very useful for the polynomial section. The idea of polynomial interpolation is like, you have these points, you want a polynomial form from them. You're going to use secret sharing in a moment, which is kind of why it's useful. So the idea behind this is you have 3 components. You got yi, you got this funny numerator, and the funny denominator. So let's just say, for instance, like you want to have like this right here. So anything that is not xi, so it's not xi, this numerator is 0. So you can't get any other value like from this expression. So the idea is like if you put, say, a particular x1, you're going to get a particular y1. You put a particular x2, you get a y2. So I'm going to erase this little mess right here. And the point of this is to fix the mess you created on the top. So say you have an xi, right? Oh, whoops, that should be, say you subtract xj and so on, right? And the bottom, I'll put this just in case to make it easier. I guess say j plus n, just say whatever other terms are in there. The bottom fixes the mess you have because this needs to be equal to 1 in order for you to get just your yi. So you clean up the mess with this bottom term here, which gives you conveniently the same result. Xi, xj, so on. Xi minus xj plus n. Do you guys get where I'm going with this? Basically, you put one particular x in, you get a particular y out. That's all that happens. And so I'm going to go through a quick example here. So based off the formula we have, we want to find each of these. So we're going to find, say, delta x1, not I. And so we know our, let's say this is x1, this is y1. So we want y1 times x minus, say, x2, x minus x3. On the bottom, we're going to do x1 minus x2 minus x1 minus x3. And so with this in mind, if we just plug everything in, we're going to get 1 to x minus, this will be 2, x minus 3, 1 minus 2, 1 minus 3. And you do this for all of 3 of your, say, delta x2, delta x3. And the idea is you sum them up. So if you were to sum up, say, this polynomial right here, let's just call polynomial x. And we'll have this be say delta x1 plus delta x2, delta x3. This is the final polynomial for which if you say plug x1, you get 1, plug 2, you get 2, 3, 3, so on. Does this conceptually make sense? Yeah.
So essentially Lagrange interpolation, it's like if you're given d points, you're taking those d points and trying to construct a d minus 1 degree polynomial that's unique.
Yes. Any questions?
And when you mod it, right?
Yeah.
That, are you gonna mod every delta separately and then add it up, or are you gonna mod the final p of x that you get from the Lagrange interpolation?
I think you could do both and be fine, to be honest.
Okay, so either one should give you the same p of x at the end.
Yeah, because let's say you get like some result like from your initial mod, right? Like say you just do like say mod n and you do like mod n for all of these and the final result's also mod n. Do you agree you get the same result at the end?
Can we provide answers in that, like,
Sorry?
Lily format?
Wait, say it one more time.
When we probably, imagine we can given an opportunity to campaign run through the branch triple H, are we allowed to provide them with an unsimplified answer like that? Because it does take a little bit of work.
Top of my head, I don't recall them actually making you do Lagrange interpolation, other than just conceptually doing it. Though I might be wrong. Either way, if you were to do it, I think unsimplify is fine. I don't honestly. I think it's easier too because like they can see exactly where you're coming from, rather than it's a simplified term that you could just make up, right? Yeah.
That's probably more probable.
Yeah. Like you did this, I think they know that you know what you're talking about. All right. Any other questions? This is good stuff. Cool. All right. So secret sharing. So the way secret sharing works, we got a few points. 1 point per person. Each person gets a key. But we want to have any m people recreated. So if you want any m people to recreate it, we will need a polynomial of degree n minus 1. So we get m unique points, so we can distribute among the people. The point is, so if you want to say make x equals 0 or coefficients the secret key, we can do it with just those n people instead of all n you gave the key to. Right, so error correcting codes. Do we have both slides? This one. It's basically scenario. Alex wants to send a message to Bob, but she needs to send packets. So you send, for example, this point and this point and this point, and then Bob can use Lagrange interpolation to decode or to make a polynomial to decode out the message. That's why we learned the previous one, so we can then do secret sharing, error codes, and we have issues. So for some reason we didn't pay enough money for Wi-Fi, and we lost a packet. And so K packets are to be lost. And so to recover from that, all we do is simply send n plus K packets. If K got lost, we still have the remaining n packets that we can use to decode. And for record, they should come from the exact same polynomial. It's not like you just make extra points up. They have to come from the same polynomial you use to generate the original endpoints. So all n plus K points are generated from the same n minus 1 degree polynomial. So corruption's a funny guy. So corruption, you don't lose them, but they get changed. So the thing is, K packets get changed. And to handle that fact, we're going to send n plus 2 packets, n plus 2 K packets. So you might think initially, why are we doing n plus K instead of n plus 2K? It's because you need extra K after that to be able to recover the K you got lost. So if we were to go through the 3 different polynomials you use for handling corruption, you have one for the error polynomial. You just know there's a certain number of errors. You need to find that. And you also know that you have a goal polynomial here, which is like the one that you want to get that was initially supposed to get like received to you. And also QX, which is your goal polynomial, which is defined, oh, it's right defined, good. It's defined right here. Basically, QX is going to be equal to the PX polynomial times the EX polynomial. The reason you do this is because eventually you want to be able to solve this QX over EX to find PX. I believe they made this on a homework. Fortunately, on the exam, as far as I know, I have not seen them force you to do this on the exam because it's kind of lengthy. But just keep in mind, this is the general process for it. Does this make sense so far? Cool. So this is practice. So we have we want to send a message to someone else on a channel size n, but this also means we can only send the most n packets across the channel. And we also know that it's a bit of a bad channel because on the first batch, you send n packets. On the next one, you lose 1 packet, so 1's corrupt. The next one, 2 are corrupt, and so on. And we want to know, well, we do this up to the n plus 1 batch. They want to know what's the max size message we can use in terms of packets that we're actually able to send. Now recall, this is corruption. So using corruption, you would send n plus 2k packets to handle it and be fine. We know this scenario, we're only allowed n packets, right? So we know when we run it the first time, run the first one, none were corrupted. And we create all of them just fine. But what happens in the second round? Because we cannot send all n plus 2k, right? We have a limited n channel. And we know 1 is corrupted, so how do we handle this? Do you have any suggestions?
Algebra to n plus 2k is how much I send.
Well, you can't send n plus 2k because the channel's limited. You have a size n channel.
Okay, so n is the amount I want to send. 2k is the amount of error, p is the amount I want to send, or some other
Okay. So would we simplify that approach to just knowing k? Like k is the only other variable I have access to. And we were to get this next iteration with just k. K and some, let's say some other numbers just for the sake of argument.
n minus 2k packets.
And y minus 2k. Besides lucky guess.
Because you need that to 2k for your margin and they're corrupting k packets, so the rest is your payload.
Yeah. Because basically we can only say that like, only the n minus 2k are actually good because n are corrupt and we need the extra. It's like k are corrupt and the other k are, well, we needed to actually find the k. So we only know that n of those packets are actually good, right? So instead of this n minus 2k, it's going to be n minus 2. The next one, we're going to have, say, to the power of 2, then to the 3, not to the power of 2, sorry, 2 times 2, then 2 times 3, and so on. So there's a pattern, you see kind of pattern here. So let's say n is 4, right? N is 4. We got 4, then we got 2, then we got 0, and then we got negative. You see where we're going with this? There's kind of a problem. We're going negative. Can you do this? And so what's the limit here? If we only go for so many, how many times can we actually use a channel? I'll just like give out just like this to make it cleaner. But pretty much you have the first batch, right? Second, third, fourth, and like say n plus 1th, right? If you just like to make it more arbitrary. For attempts like 0 through 2, you have like at least like more than 0, like or more equal to 0, like uncorrupted packets. But then if you're less than next ones, you go negative. So what you do is just make a summation for only the first half. Like this one, like the first half that are like not 0, and that's like not negative. And that's the amount, like a maximum I can send through the channel. Does that make sense? Sorry, is there any questions?
The question was asking how many total packets we're gonna be able to.
It's like the max, yeah. Like what's the max you can actually send? Like given this limitation. Okay. Cool. So your second error type of corrupted, basically you just use this funny formula here. For every pair of points you do have, you can solve this equation for qx equals yex. And the idea is that it will be 0 for which it's an error. Like this week 0 is an error. That's how you know. And pretty much it. Pretty much what I said before. It's not much different. A few reminders of the formulas here because you're gonna be using this in the next problem. Whoa, okay. That was a good solution. That was bad. Can you guys see screen? Cool. So I know it's like a little low. Do you want to erase it? I just don't want to leak the answer. Okay. So given endpoints, what's the max value of D such that there is at least at most 1 degree D polynomial that passes through at least M1 is K data points. I'm actually realizing it is almost 5 o'clock. Do you guys want to do this real quick, or do you want to just go to counting?
Let's go to
Counting? Alright.